Good evening, everyone. My name is Joanna Wu, and I am an astrophysicist at SFU, at Simon Fraser University, in the Department of Physics. I'll just show you a picture of me. That's me right here. So I am live streaming from the Trottier Observatory at the Burnaby campus of Simon Fraser University, and this is our webpage. You can read more about the observatory here. For those of you who are part of our loyalty program, the good news is you can use attendance at this live event for credit towards your telescope. So this is relevant for those of you who already have received a loyalty card from the program. So what you need to do is you need to send a list of every object we will look at tonight to this email right here, sfuscienceoutreach@sfu.ca. So send that list to this email along with a photo of your loyalty card, and send it there by tomorrow at midnight. So by Saturday midnight. You have a little over 24 hours to do that. All right, so let's get started. What are we looking at here? Okay, so as you see in this image right here, at the top, the very top webcam here is an interior camera inside the dome, and you can see the telescope is the dome. The slit is already open, and the telescope is bent all the way almost to its maximum because we're looking at an object that is about to set in the west. What is that object? Let me close this window and let you see. So that's what we're looking at right now. What is this? Is this the moon? No, because the moon is actually full right now. It's on the opposite side of the sky. We are looking towards the west, and this is the planet Venus. So Venus, if you have a window that's pointing west, or maybe a bit northwest, or even north, and if you crane your neck a little bit, look in the sky. The brightest object there, the brightest thing you can see in the sky, that's Venus. That's the planet Venus. In fact, Venus is so bright that you can actually see it in broad daylight with your own eyes. I've seen it before in broad daylight, actually. Right now, Venus is the evening star, so it's in the west after sunset. But in just past June, actually, a few weeks into June, you'll start seeing it in the morning sky. And that's actually how I was able to see it with my own eyes. I had to wake up early before sunrise, find Venus in the morning sky, and then followed Venus with my eyes past sunrise, and then I could track it that way. So you can actually see it if you know where to look. So that's how I was able to do it. So Venus, as you can see, is a crescent. Why does it look like the moon? How strange is that? Okay, well, the reason why Venus has phases like the moon is because it's closer to the sun than we are. So if you can imagine the planet Venus being between us and the sun, like if it's exactly in the middle between us and the sun, then we'll only see the dark side, right? But if the planet actually moves a little bit away from right between us, then you'll start to see a little bit of light on its side, and that's the crescent right now. So that's what we're seeing. The crescent phase of the moon. Now, I forgot to mention actually that I do have the chat box open, so I will try my best to follow to see if you have any questions, and I'll try to answer as many as I can, but I am probably going to miss a lot of them. So I have a couple of helpful assistants here on the chat box who are monitoring, and their names are Rohit and Sarah. And they are staff members at the Trottier Observatory, and they will be answering questions that I miss. So hopefully I'll be able to answer questions that you have, but my assistants will be able to help me as well. Okay, so this is the planet Venus. So as you'll probably see as we get later in the day, so it's 9:30 here in Vancouver, and the sky is still really bright. You can see in the middle camera here, the western sky is still very bright. We can still see Venus, which is nice, but it will be it will stay bright for a little while longer, unfortunately, and this is only going to get worse until June 21st, and we'll have to stay up later and later in order to see anything in the sky. But that's okay, because there are lots of things that we can see in the sky tonight. All right, so the planet Venus isn't the only planet that has phases. Actually, Mercury does as well. So the planet Mercury is also closer to the sun than we are, and it also has phases, but it's a lot harder to see Mercury. It's a bright planet, but it usually stays pretty close to the sun, so it's really hard to find it in the sky. But Venus can extend pretty far out, so you can see it with your eyes pretty easily. Yeah, so Venus actually, even though it's the second from the sun, fun fact, Venus is actually hotter than Mercury. So Mercury is the closest planet to the sun, then Venus to second, but the temperature on Venus is quite a lot higher than Mercury, and the reason is because Venus has a really thick atmosphere that went through a runaway greenhouse effect. So it's really, really hot on the surface of Venus. But Mercury, which doesn't have an atmosphere at all, isn't as hot. So the surface on the light side is quite hot, but it's not as hot as Venus. So that's a fun fact that I thought of sharing with you. Okay, so let's see, the phases. So okay, it's true that Venus and Mercury aren't the only planets that have phases. Mars has a tiny little bit of phase, but it's so unnoticeable that I'll just say kind of imprecisely that no other planets have phases like Mercury and Venus. Okay, so what else can we see in the sky besides the planet Venus? Well, I have a pretty cool lineup of objects for you. And the next one we will be looking at is an object called a globular cluster. And it's labeled by a catalog number called M3. Okay, so this is a very convenient piece of software where I can just type in find and it'll find it for me. And then let's center it on M3. It's right there. So it's actually, this piece of software shows you where you're looking at. So it's in the east, between east, southeast, and southeast. M3 is this object right here. In between, excuse me, in between the constellations of Bootes and Coma Berenices. So M3 is, because it's called, the M in front of it stands for Messier because it's part of the Messier catalog. Messier, so Charles Messier, was an astronomer that lived in the 18th century who cataloged about 100 and a few objects that looked like fuzzy objects in the sky. And so this M3 was actually the first one that he discovered. So let's go to it and take a look at what this is. So you can see as I clicked on slew over to that object, the telescope has moved. You can see the telescope has pointed over to that region of the sky. Now the dome is going to take a while to catch up. The telescope moves quite a lot faster than the dome itself. So let's wait for that to catch up. But you can already see here in this label that M3 is a globular cluster. So let's take a look at what this globular cluster looks like. Okay, let me take a look at the chat box. Right, okay, so some people are talking about other planets. So yes, there are, the order of the planets from the sun goes Mercury, Venus, Earth, then Mars, Jupiter, Saturn, Uranus, and Neptune. Pluto used to be a planet, but now it's a minor planet. It used to be called a planet, but now it's categorized as a minor planet. Okay, so are we there yet? We are there, look at that. Okay, so we are at M3, the dome has caught up, sorry, I can't speak. And let's look at what the globular cluster looks like. Okay, so that was a 1 millisecond exposure, which was good enough for Venus because it was so bright, but we actually need a longer exposure for this cluster. So let's see, actually I want 20 seconds. A 20-second exposure, and let's start the live stack. Actually, I can't see the bottom of the screen. There we go. Okay, let's adjust the viewing. And the sky is still quite blue, which means it's still bright out. But that is okay because we can set it, whoops, excuse me about, sorry. Okay. Now, the sky, oh look, it is stacking. It is stacking, but I need to adjust to the colors here. The sky is still very bright, so unfortunately there's going to be a lot of blue in the image. But hopefully adjusting the colors will allow you to see more of the more of the colors. Okay, well, let's bring this, let's make this brighter. Okay. This is a globular cluster. What is a globular cluster? So a cluster of stars comes in, there are two types of clusters of stars. One in which all the stars are gravitationally bound together, and so those are called globular clusters, and the other ones are called open clusters. So globular clusters are quite massive usually, and there are usually thousands of stars in such a cluster. These globular clusters are found usually in a halo around the galaxy. So what is a galaxy? So the Milky Way is a galaxy. The Milky Way, you can see a band going across the sky. I'll show you a lot more pictures of galaxies tonight. But galaxies, well, our galaxy at least, consists of about 100 billion stars. And globular clusters, so our galaxy is shaped like a disk, and it's got spiral arms and like a plate, like a disk like a plate. But globular clusters, as well as other stars, tend to be distributed in like a round halo around the galaxy. This particular cluster is about, so if you imagine a dinner plate that's a circle, the center of the galaxy is the center of the plate, then we are about halfway between the center and the edge of the plate. So that's our orbit, the sun's orbit around the center, about halfway. So if you imagine that distance, take that same distance but put it up above the plate, and that's approximately the distance of this globular cluster. It's actually a little bit farther than that. But it's above the plane. So most stars are within the plate of the Milky Way. But globular clusters such as this one are actually located around in a halo. Okay, so this, unfortunately, the sky is still kind of blue, so it doesn't look the best in this image. But let's try to adjust it a little bit and see if any of this looks better. Okay, I'm going to clear it and try it from the beginning. Maybe it's darker now. It is darker now. Let's try a new stack. So what this piece of software is doing is actually taking a bunch of frames of 20 seconds each and stacking them, so aligning where all the stars are, and stacking them so that we can add up the signal from the stars and and account for the noise in the sky. So that's what stacking does. It stacks a bunch of different images together. So we're taking multiple exposures, and this is what it's doing. It's still too red. Okay. Okay. Actually, I'll move this one over. So now you can see. Now you can see the. Yeah. So as the picture, as these frames stack, you'll see that the sky noise starts to decrease. It's kind of a nice, nifty little feature of this particular software, this live stacking. Okay, so let me see if there are any questions here. Okay, whoops, what did I do? Okay, well, it's stacking. Sky is still quite blue, but you can basically see that there are lots of stars in this image. There are about this cluster is actually about 12,000 solar masses, so it's probably got about 12,000 stars. So it's about 11 giga-years old. So globular clusters are very old compared to the stars in the disk of the galaxy. They're the oldest. They're among the oldest structures in the universe, actually. 11 billion years old is almost as old as the universe. The universe is about 13.6 billion years. So globular clusters are extremely old. Okay. Let's see. Yeah. So as you can see, as the images get stacked here, you can see that the sky noise is decreasing more and more, and you can see more of the dimmer stars in this image. Okay, let's see. Okay, what do I mean by sky noise? That's a very good question. So the sky is quite bright. So if I actually, the first image I showed was of the planet Venus, and it was like a 1 millisecond exposure. But if I had exposed it for longer, Venus would have been overexposed and you would have seen a blue sky. So the sky actually shines in light. So when the sun has completely set and it's completely dark, you still get light from the city. So the city shines light into the sky, because unfortunately our lights go up instead of down, and it makes the sky shine. So the background light in these images is not zero. So there's actually a source of light in the sky. And but that sky noise can be subtracted, and the more images that you stack, the more that you stack images, the greater your what we call signal to noise in astronomy. So your objects become brighter compared to the noise in the sky. Yes. So somebody noticed a bright star in the sky in the west. Yes, it's about slightly to the northwest, actually. That is Venus. It's the brightest thing that you can see there in the sky. Okay, so let's make a few adjustments to this image. And I'll be able to save it in a minute. Okay, so, oh, that's a very good question. Somebody asked, What movement pattern do the stars have in a globular cluster? That's a very good question. So they do orbit around their center of gravity, but the orbits are random, so they aren't rotating around in a pattern like a disk, like the Milky Way. Like all the stars in the Milky Way are orbiting in a certain plane, but a globular cluster has more random motions. So the orbits are circles or ellipses around the center of gravity, just like they would be in any kind of or any kind of gravitational field. How do you calculate the age of the universe? Wow, that's a great question. Okay, so one of the things we know is that the universe is expanding. So you can see that the galaxies all around us are moving away from us in such a way that's consistent with uniform expansion. So one thing you can do is, if you know the rate of expansion today, you just kind of wind back the clock and you can infer the age of the universe that way. So it's a bit more complicated than that, of course. You have to take into account that there's a little bit of acceleration today. The universe is not just expanding, but it's accelerating in expansion. But you have to take it into account a bunch of things, but that's basically the way we know the age of the universe. Okay, wow, this stack is looking pretty nice. So this is the globular cluster M3. Okay, so I'm going to move on. I'm going to save this image, and I am going to move on to another object. So as I told you, I am an astrophysicist, and my specialty in astrophysics is galaxies. So that's what I research. It's my bread and butter. It's my absolute favorite thing in the world is galaxies. I love galaxies. So if I were to sing a song about my favorite things, it would be about spiral galaxies and elliptical galaxies and lenticulars and those kinds of things. Okay, I'm not going to sing for you, don't worry. Okay, so what's our next object? Well, let's see. So, okay, the Milky Way is a galaxy, so so do I have a picture of the Milky Way here? I do. So this is a picture of the Milky Way, from Earth, and this is actually from Wikipedia. And you can see these gorgeous dust lanes. So that's what it looks like from inside a galaxy, but most of the galaxies that we see outside, they're farther away, and they're going to look, smaller, and we won't be able to resolve the individual stars. But the first galaxy we're going to look at is a spiral galaxy, kind of like the Milky Way, and it's also a Messier object. So the Messier objects that start with M are among the brightest objects in the sky, fuzzy objects at least in the sky. So this will be our next target. It's actually pretty high in the sky. Right now it's pretty close to the Big Dipper. So this, so this is the this is the area of the Big Dipper, and so this is the cup of the Big Dipper, and this is the handle. The two end stars point to the North Star, right? So the galaxy that we're going to be looking at is actually in here. It's part of an interacting pair of galaxies, but it's actually the biggest galaxy in a group of galaxies. So let's go over there. So while the telescope is moving first, and the dome will catch up. So while it's getting there, I'm going to talk a little bit about the... Oh, I forgot to... Let me see, I saved those images. I'll take a screenshot. Okay, good. So while we're moving there, I'm going to zoom in on it. This is a pretty neat little group of galaxies. It's a nearby group. So our galaxy, the Milky Way, is also in a group of galaxies called the local group, of course. And the biggest galaxy in our group is the Andromeda Galaxy, where it's about 2 million light years away from us, and we're the second biggest galaxy. The Milky Way is the second biggest galaxy. But we also have a bunch of satellite galaxies in our group, little small dwarf galaxies. So it's the same thing with this group here. M81 and M82 are two of the biggest galaxies. I think there might be a third one that's of comparable size. But it's surrounded by a bunch of little galaxies as well. So this is the M81 group. So we're going to be looking at both of these because they're both really interesting galaxies. Okay, we are there. The dome is there. Okay, so let's clear this and make a stack. So M81. So I'm going to probably have to do longer exposures. Actually, that's not that bad with 20 seconds. The sky is still a little bit blue. It's still kind of bright, but let's adjust the colors a little bit. Okay, and it's stacking. This is wonderful. I think we're going to need to have longer exposures with this one because it's a bit of a dimmer one. Okay, let me move this over as well. Clean it up a little bit. And move this down. Actually, well, let's stick with 20-second exposures and see. Let's see what happens when it stacks these. Okay, so as the exposures keep stacking, we'll start to see more of the faint outer spiral arms in this galaxy. So this is it's quite a beautiful galaxy. If you could see, I'm actually going to take. I think I'm going to take. No, I'll have to just keep adjusting the colors every so often. So the outer spiral arms, if we can get that, if we can start to resolve some of the dimmer parts of the arms, we can see kind of blue spiral arms in the outsides. So this galaxy has this really prominent bulge in the center. Galaxies traditionally have been decomposed. Traditionally, it seems like galaxies have multiple parts in them. So I talked about with the Milky Way, I talked about a disk, the disk component of galaxies. I also talked about a halo of stars. The halo of stars doesn't really contribute a whole lot to the mass, but what does contribute to the mass of a galaxy is the central bulge. So the Milky Way has a bit of a bulge. This galaxy here, M81, has a rather massive bulge. It's got quite a large bulge, and the mass in the disk is less significant. So let's see, how are we doing? Maybe I can push this down a little bit. See if we can see any of the outer spiral arms. There's a little bit, I don't know if you can see it on your screen, but I can see a bit of an arm right here, a bit of an arm here. I think I need to bring the red down a bit. Okay, so if I do that, you can see that the inner regions of the galaxy are red. The outer regions have a brighter bluer part. It's hard to see with this right now, but well, let's wait for the frames to stack a bit, and then it'll probably become a bit clearer. So the stars in galaxies, especially in the centers of galaxies, the bulge regions of galaxies, tend to be red. Now, why is that? So if you see a blue star, blue stars tend to be the most massive ones. Blue means hot, right? So if you think of a flame, a blue flame is hotter than a red flame. A blue star is a very massive, very hot star, And blue stars don't last very long. So if they're really massive and hot, they will run out of their fuel much faster than a small little star. So a blue star will not live very long, but 100 million years. That's considered very short in astronomy terms. And then they'll go supernova, die out, and you won't see them again. So if you see a blue star, you know it hasn't been around very long because they don't live very long. So, but if you see red stars, that means, so in this galaxy, if the inside, whoops, excuse me, if you see the inside of the galaxy is red, it means that there are no blue stars there. So it means that it's no longer forming any new stars. So the population of stars in the centers, if they're red, the population is likely to be old. So let's adjust this a little bit more. I wonder if we can start to see a little bit more of the outsides. Yeah, it's starting to look a little better actually. But I think it's easier to adjust this. I'm going to adjust this color slightly. Okay, so I'm adjusting the color quite a lot, so you may not believe me, but because sometimes it looks red, sometimes it looks green, depending on how I adjust it. But okay, so we'll see. We'll see when these arms start popping out. The arms are bluer than the inside. So if the spiral arms are blue, it means that they've got young stars. So it's actually forming stars in the spiral arms. So that's where we see new star formation in galaxies. It's in the spiral arms. And that's where, in the Milky Way as well, the new star formation, the star formation rate of the Milky Way is about 3 solar masses per year. So the Milky Way is forming stars, and it's forming at that rate, about 3 solar masses per year. So galaxies about the same mass will approximately form stars about that rate. The Milky Way might be slightly lower in its star formation rate compared to its mass. But yeah, so we're starting to see a bit more detail. This galaxy also seems to have shells around it. I don't know if you can see, but I can see on my screen. I can see little layers and shells. What's interesting about this galaxy, so I told you that M81 is interacting actually with another galaxy nearby called M82, right? So it's the next one nearby, and we're going to see that one next actually. And so it is interacting with it, and it's in a group that's got a lot of galaxies in it. So very likely these shells are a result of interactions with other galaxies, probably its dwarf companion galaxies. Okay, so let's start to see. I'm going to move this one slightly over. See, you can see a little bit of detail in this galaxy. Oh yeah, see, you're starting to see the arms here, and here. It's a very pretty galaxy, in my opinion. Let's move it over a little bit. Okay, I haven't looked at the chat box in a while. Let's see. Does a star become blue then red? So, so what happens is, actually, you're right. So blue stars are the most massive stars, and then they eventually do become red giants, actually, and then they eventually explode. So the most massive ones eventually explode. So so yes, they do become red at some point in their lives. But that phase is very short-lived. So if you see a red star, chances are it's one of the long-lived little ones. Oh, what galaxies have red arms? Oh wow, that's a great question. Okay, so what galaxies have red arms? Galaxies that have died out their star formation, like if their star formation has completely died out, and there are many reasons why that might be, but one of the main reasons why that might happen is because Sorry, I just lost my train of thought. Okay, so there are a couple of theories as to why galaxies stop forming stars. It's actually the main thing I study actually. So one of the and we're going to look at one of those galaxies in a minute. What time are we at? We're at 10 o'clock. Okay, so the black hole in the centers of all galaxies are thought to produce an enormous amount of energy that either uses up or blows out or heats up all the gas in a galaxy. And in order to form stars, you need gas. So if you're going to remove gas from your galaxy, then you'll stop all your star formation and you'll end up with a red galaxy. So the galaxy disks actually aren't really shaped in spiral arms. They're actually more like disks, to be honest. But it's the new star formation that seems to happen in spiral arms because of the density, the extra density that the spiral arms happen in. But eventually, the stars that are even formed in the spiral arms eventually rotate around, and the pattern, like if you stop all the star formation, that pattern will eventually disappear and it'll become kind of a flat disk. And it'll turn into something called a lenticular galaxy because it looks like a lens. So it's a very good question you asked. Spiral arms generally are blue because those are the sites of new star formation. Okay. Okay, so this is looking pretty good. This is M81. It's actually looking better on my YouTube screen than it is on this other screen. Okay, cool. I'm going to adjust it just a little bit more. I'm going to save it and move on to the next galaxy because the next galaxy is really, really cool. So we don't want to miss that one. Oh, it's really pretty. One more this way. Yeah, that is all right. Maybe I'll move this slightly over as well. No, that's too much. Okay, I think I will save that galaxy. No, that's too much. I'm going to keep adjusting it. Oh, that's alright. This is a pretty good image. No, sorry. Okay. Yeah, that's all right. You can see quite a bit of the spiral arm. Okay, I'm going to save that. And okay, perfect. Now, what's the next galaxy we're going to look at? It's the one right next door. M82, the Cigar galaxy. This is really cool because this is a spiral kind of disk galaxy that's viewed edge on, so viewed from the side. So let's clear this one, and let's see, I'll probably have to clear it again because it was moving during this exposure. Okay, let's do it again. Okay, let's see what somebody has said. Oh, somebody asked what planets are in galaxy M81. Well, we haven't discovered any planets in that galaxy, unfortunately. That would be cool, hey? But we're only still looking at planets in our own galaxy. And that's still, we're still trying to count those. And we only barely have images of these, so it'll be very, very difficult to actually find any planets in another galaxy. We can't even see the stars, really, inside of M81, although I think the Hubble Space Telescope did resolve some stars in M81. But it would be extremely difficult to see planets in other galaxies. It's already quite difficult to see planets in our own galaxy. Okay, let's see. This is M82, and it's not looking very nice yet. Okay, so this is M82, and it's really neat because if you're looking at it from the side, it's called the Cigar Galaxy because it looks like a cigar. But what's really neat about this galaxy is that it's got a huge starburst of new stars. Now, why does it have... Okay, it's good stacking. It's good. Okay, why is it undergoing a starburst? So it's, as I said, it's interacting very closely with M81, the bigger galaxy beside it, and while it's going through these orbits, it experiences these tidal forces that push all the gas in the galaxy towards the very center of the galaxy. And so if it pushes all the gas towards one spot, it creates this high density region where it can't help but form lots and lots of stars. So it turns out that the star formation rate in M82 is about 10 times higher than the normal star formation rate of normal galaxies. So, like the Milky Way. So it's, it's 10 times higher than the star formation rate of the galaxies that are of its mass. So our galaxy is a bit more massive than M82, but so our galaxy has a star formation rate of 3, but the star formation rate of M82 is higher than 10, so it's pretty high. But for its mass, it's a less massive galaxy. So the gas is being funneled due to the gravitational forces. So the gas is not only just feeding the starburst. So the starburst, you can see evidence for the starburst because actually you see these gases that are actually flowing out. You can see a lot of dust in this galaxy. The reason why you see dust in galaxies that are star forming is because dust grains, anything, so the universe, when the universe was formed, it just had hydrogen and maybe some helium and maybe some trace amounts of other elements, but it was mostly hydrogen and helium. And so when stars form, it's mostly going to be hydrogen, but when stars form, there's a lot of gravity in the center of, in the star itself, but most of the pressure is on the center of the star, its core. So that core, it's because of all the heat and pressure, there's enough energy to ignite nuclear fusion of hydrogen into helium, but it only happens in the core of the galaxy. But as the star runs out of hydrogen in the center, then it starts burning helium into heavier elements like carbon and oxygen, and even heavier elements if the star is really, really massive. So when the star becomes a red giant, the outer layers of the star float away, but if a star goes supernova, then all those heavy elements like iron and the other ones I mentioned will be spread out in the what's called the interstellar medium, in the gases in the galaxy between the stars. So the grains of like silicates and dust are actually formed in the outer layers of red giant stars. And so that's why you need to have young stars that are forming in order to actually have dust grains. So you'll find that star-forming galaxies tend to be very dusty. So this galaxy is quite dusty. You can see these dusty regions that are blocking, and actually the Milky Way has a lot of dust too. There's a picture of the Milky Way, and look at all these dust lanes here blocking the light of the Milky Way. So it's not just other galaxies, it's ours as well. Okay, so let's go back to M82. There's M82. So you can see if we had higher exposure, and if we looked in different wavelengths, you could see this amazing plume of gas flowing out basically on either side of the disk in these two cones. And the gas is coming from the starburst, because when you have like a ton of stars, especially these really young massive stars, they give off a lot of solar winds. Like our sun actually gives off a solar wind, but the ones from the really massive blue stars are even more powerful, and those winds are actually seen in this galaxy. You can't really see it that well here, but you can kind of see a little bit of it here. You can see a little bit of the winds. It's reddened because of the dust, but you can see a little bit of the wind coming out from here. Let me see if I can enhance this image a little bit more. Okay, well, that's not bad. Yeah, so that's M82. Oh yeah, you can see a little bit more too. You can see a little bit more of the winds right here. It's beautiful. Oh, such a beautiful galaxy. Okay, was there anything more I wanted to say about M82? Oh yes, that's right. Okay, so the gas that's been pushed towards the center of the galaxy due to the tidal interactions with M81, the big nearby one. So those gravitational forces push the gas inside. So the gas is not just feeding the starburst, it's also feeding the supermassive black hole in its center. So actually there have been some studies showing and arguing that there is a very weak active nucleus in the center. So every galaxy has a black hole, but not every black hole in the galaxy is active. So this one probably does have like a kind of a weakly active. It's active, but it's only weak. It's not like one of the powerful ones, which I'll show you next actually. But this one is probably a weak nucleus. And it's, but yes, that's one of the ways that if the black hole does become more active in the future, that's one of the favorite candidates for how you might actually remove all the gas from the galaxy and eventually cause the star formation to stop in this galaxy. It's one of the favorite methods, but it's not necessarily the way that it happens. So that was M82. Let me look at the chat box. Wow, there are people watching from Australia, and I'm sure I probably missed a lot of what people are saying. I'm really sorry that I'm not looking at the chat box all the time. So, why is the expansion of the universe accelerating? Wow, great question. So the fact that the universe is accelerating in its expansion is something that's an observed fact. Like we just know that because we can measure the expansion and we can measure that it's accelerating. So the fact that it's accelerating, we just think it's due to something called dark energy. And what is dark energy? We have absolutely no idea. So dark energy is just the thing that causes the acceleration of the expansion. So we observe that it's accelerating, but we don't really, whatever the reason is, we just call it dark energy, and we just don't know why. So the short answer to your question, Morgan, is that we have no idea. We don't know what dark energy is. So, but there are lots of projects that have been proposed that are looking to study that, to find out a bit more about what this dark energy is. So, yeah, okay. This is so pretty. Let's see. How are we doing in our list? So I have a few more cool objects to show you. So I might move on from this object. Let me just adjust it a little bit and save the image because it is so pretty. I think you probably move this back a bit to get more detail. Wow. Yeah, that's too much. No, actually I had it better before. Let's see. That's all right. No. There? Yeah, that's pretty good. Oh, it's beautiful. Beautiful. This is a 10-minute stack. Okay, let's save that. Take a couple of saves. Okay, that was M82. Very pretty. Okay, so what is our next object? So actually this is, okay, I am going to be showing you a lot of galaxies. It's not only because galaxies are what I study, it's also because the galaxies are the things that are visible right now. Like these are the brightest objects that are visible right now. So let's go to a galaxy called M87, also a Messier object. It is the center of the Virgo cluster of galaxies. So it is the nearest cluster to us. The cluster is about 50 million light years away, and the galaxy is about that too. It's the largest one in the center of the cluster, and this is a cool galaxy because I showed you two spiral galaxies. This one is not a spiral galaxy. This is an elliptical galaxy. So let's take a look at it. Oh wait, are we there yet? The dome has to catch up. Let's see if the dome is caught up. Not quite. So this is an elliptical galaxy. So there are roughly two types of galaxies. There are spirals and there are ellipticals. So these ellipticals, and you'll see it, they're called elliptical because they're round. So they're basically shaped like balls, like basically like a gigantic globular cluster, but a globular cluster with dark matter. Okay, so now somebody's going to ask me about dark matter. Okay, you can, feel free to ask. Well, let me talk about this galaxy. This galaxy is a gigantic galaxy. It's quite big. First, let's clear this and take an image. I want to make sure I have the correct settings for it. Okay, so there is the galaxy. It's not very bright yet. I might have to take a longer exposure actually. Let's see if the next one stacks. No, this one stacks. This is good. Okay. Oh, we're gonna have to take a longer one in order to see. Well, we'll see. I think you will be able to see the jet out of this galaxy, maybe with a few more exposures. You know what? No, I'm going to clear it. I'm going to do a 60-second. I'm going to do a 60-second exposure. That'll be better. And I think I might need to adjust. Oh, actually, that's already what I want. Okay, well, let's see. Let's see how this one does. This is a bit long. I mean, it's a dim galaxy, so I have to take a longer exposure for us to see any detail. Let's clear this one first. So this will be our first 60-second exposure. Okay, so let's talk about the elliptical galaxy. This galaxy is the famous galaxy where we were able to take our very first image of a black hole. So as I mentioned before, every galaxy seems to have a supermassive black hole. Maybe there are a couple of exceptions, but the vast majority of galaxies have a black hole. Our galaxy, the Milky Way, has a supermassive black hole, and it's about 1 million solar masses. I mean, that's how massive it is. I mean, it's crazy. It's huge. The one in this galaxy is 1,000 times more massive than that. Oh yeah, you can kind of see it a little bit. So you can it's hard to see in this image, but we'll wait for the stack to continue. But you should be able to, as this becomes clearer, you should be able to see the jet. I can kind of see it already. I want this to be brighter. You can kind of see a little bit of the jet right here. I don't know if you can see that. But yeah, this black hole is 1,000 times more massive than the black hole in our galaxy. It's pretty crazy. And that's the black hole that we have an image of, our very first image of a black hole. Yeah, it's pretty neat right there. So, okay, so this is an elliptical galaxy. It's hard to see any detail right now, but as we stack more images, we'll be able to see a bit more detail. It's round, as I said, and it's red, so it's not forming any new stars. And the fact that it has a jet coming out of its center means that the black hole is active. So what does that mean, that the central black hole is active? If it's active, it means that it's eating up a bunch of stuff. So So, I mean, you know, black holes have a lot of gravity, right? So it's going to be sucking up a bunch of material. But the material isn't going to just go straight into the black hole. The material is going to spiral around in a disk first, right? So all the material spirals around into a disk around the black hole that we call an accretion disk. That accretion disk is moving around so fast, the energies are enormous. So it's moving around really, really fast. It's causing a ton of, you can think of it as like friction. A lot of energy is built up in that disk that gets released into this really powerful jet that's sticking out of the galaxy. And that jet carries a lot of energy, and it emits, it's a very bright radio source actually, it's quite bright. And that energy keeps the gas away from this galaxy. That's the theory anyway, that the energy from the black hole and the jet is keeping the gas too hot to fall back into the galaxy to form new stars, and that's why this galaxy is dead. At least that's the most popular theory as to why this galaxy has stopped forming stars, or as to why elliptical galaxies in general have stopped forming stars. Why is it elliptical and not spiral? Right, that's actually quite one of the strongest correlations between like a galaxy that's forming stars and not forming stars. Like the biggest prediction that you can make is that the galaxies that are forming stars are disks, and the galaxies that are not forming stars are round, they're elliptical, and they're dense. So, and that's a big question actually. It's a huge question, but one of the reasons why we think galaxies become round in the first place, like we expect galaxies to be disk-like because when gas falls into a galaxy, it spirals around in a disk. It's to do with angular momentum, the thing that causes figure skaters to rotate faster or slower depending on if their arms are out or in. Anyways, that quantity of is what is the reason why galaxies tend to be disks. But why are these elliptical galaxies round? One of the ways you can get around galaxy is through mergers. So if you have two galaxies that merge together, especially if they're, it depends on how much gas they have, but aside from those details, if you have two merging galaxies and if they're, orientations are random, merging galaxies generally produce round galaxies. But merging galaxies also tend to feed a black hole. So some of those things are reasons for which a lot of people think that the black hole is responsible for turning off the star formation in galaxies. So how are we doing here with this image? Let's see if we can do a few more adjustments to see more of the details. Okay. Oh yeah, if I actually dim this a little bit, you can see more of the jet here, because the jet is actually quite bright. Oh, let's enhance this. No, maybe not. Actually, it's better, in order to see the jet, it's better to have the high end higher. Yeah, let's see. Nope, too far. Still too far. Yeah. Anyways, I could do this for hours. Too bad we only have half an hour left. Okay, let's speed up a bit. Okay, well, we don't have to see everything on this list. There were a bunch of galaxies. Actually, this will probably be the last galaxy we'll look at. Actually, there are lots of cool things. I mean, maybe we can do one more. Before the Ring Nebula. I do want to show you the Ring Nebula. The Ring Nebula is so cool. Okay, but let me adjust the settings here, save an image, and then I can move on to something else. very pretty, but I think I'll go, yeah. This actually looked a little bit clearer the other night, but that's alright, this is pretty good. Okay, that's alright. Okay, that was M87, the central black hole. Wait, let me just take a look at the chat box. Oh yeah, no, we don't have adaptive optics. Adaptive optics is actually quite complicated and quite expensive. Actually, here in Canada, we're designing the adaptive optics system for the 30-meter telescope, actually in Victoria. So it's quite the project. It's quite a complicated thing. So we actually don't have a system like that here at our little observatory. Okay. Okay, oh, somebody asked for the Horsehead Nebula. Actually, the Horsehead is not visible at this time. It's a winter thing, so unfortunately it's gone right now. It's gone, it's set below the horizon now, so we can't see it. So how come black holes and ellipticals aren't black? Oh, they are actually. So the image of the supermassive black hole, should I Google it? Wait, we don't have that much time left, but that's okay. Let's just quickly Google M87 black hole. So yeah, how about this one? Yeah, see, there it is. So okay, there's a lot of light that has bounced around in here, but yeah, the center regions, I mean, the black hole is black. Like, light cannot escape from a black hole, so it does look black. So what you're seeing here is light that's going okay, it's light that's going around the black hole. It's seen from the other side of the black hole that's being lensed around the black hole because of gravitational lensing, because gravity acts like a lens. So, but where the black hole is, it really is black. The gravity in a black hole is so strong. So if you can imagine the Earth, right? In order to escape the gravity of the Earth, you have to fly a rocket at a certain velocity. I think it's like 11 meters per second. But if you have a more massive object, then you need to fly away even faster than that. A black hole is an object where you have to fly away faster than the speed of light in order to get away from its gravity. So even light, which is the fastest traveling thing known in the universe, cannot escape a black hole, and that's why black holes are black. So yes, they are black. Okay, so let's move on to our next objects. So the next one actually is the Ring Nebula. I think it should be high enough to see right now, but it is a little bit low in the sky. The Ring Nebula is in the constellation of Lyra, and it's where Vega is. This is the star Vega, which is the famous star that was in the movie Contact, where the aliens were from. But it was fictional movie, based on a work by Carl Sagan. The Ring Nebula is right there. So actually, let's see how high it is. I think it should be high enough for us to see right now. Yeah, it is. It's really low. It's really near the edge of our ability to see it, but let's go there. Okay. Okay, so the Ring Nebula, so we're going back down, so we were talking a lot about galaxies. Galaxies are these huge things, like 100 billion stars, right? Like our Milky Way is about 100 billion stars. Huge. So now we're going back down to an object that's about the size of a star. So this is the Ring Nebula is actually the remnants of a dying star, a single star used to be a red giant, and its outer layers have floated away. So let's take a look at it. It's pretty cool because it's really, really colorful. Let's clear that, and we will do a shorter exposure. Let's clear that. Let's do it again. Yeah, so as I mentioned before, when stars get to the end of their life, so that when they run out of hydrogen in their cores, and then they burn helium, and then they run out of fuel in their cores, they expand to become a red giant. And those outer layers of the red giant expand to, let me just adjust this for a second. I think we might not, let me just reset this. Yeah, I think we're still too low. Okay, let's look at another object. We're too low in the sky. Okay, that's a really colorful one. We'll get to that at the end of the night. So let's go to the other galaxy that I really want to show you, which is really cool. M64. M64 has a nickname. It's called the Black Eye Galaxy. And you'll see why in a minute. It's pretty cool. Okay, let's wait for the dome to catch up to the telescope. Okay. Okay, there you have it. Starting to get a little bit of dew there on the side, but let's, okay, I'm going to need to do a longer exposure for this one. So the Black Eye Galaxy, you may have seen the glimpse of it. It's got this enormous clump of dust right in a certain area, so that it makes the galaxy look like a black eye. So that's why it's called the Black Eye Galaxy. So just like the Milky Way, I showed you the Milky Way has dust. Same with M82. M82 had a big, had a lot of dust in it. This galaxy has so much dust in it that it looks like a black eye. It blocks a lot of light. So it's pretty cool. It's a spiral galaxy, and it's got a lot of this is actually a really cool galaxy. It's really interesting because this galaxy has, so the stars are all rotating one way. They're all regularly rotating, but the gas seems to have two components. Part of it is rotating with the stars, and the other part of the gas is rotating the opposite direction. Very weird. It's very, very weird. So people think that the reason why the part of the galaxy, so you can see it, look at that. So if you turn your head 90 degrees to the right, it kind of looks like a little bit of a black eye right there. So it's pretty neat. It's pretty neat. You can see that dust right there. Okay, so the reason why astronomers think that there's gas in it that's rotating the wrong way is because it probably had a satellite, a small dwarf galaxy that collided with it, but rotating in the wrong direction, and that galaxy probably had a lot of gas, which then got eaten up by landed. All the gas got sucked into the bigger galaxy M64, the Black Eye Galaxy, and that's why we have a lot of gas in this galaxy that's rotating the wrong way. So that's the reason why we think it's got gas rotating the wrong way. Okay, yay! So there's the Black Eye Galaxy. Let me just adjust this slightly. There, that's good. so pretty. It's so neat we can see this detail. Look at all that dust right there. It's a spiral galaxy, so you can actually see some of the arms coming around as well. Okay, I haven't seen the chat box in a while. Okay, so yes. Yes. So somebody asked that they're predicting that our galaxy is in collision with the closest. Yes, that's true. We are going to collide with our closest galaxy, which is called the Andromeda Galaxy. We do, it'll happen in, I think, something like 5 or 6 billion years from now, so you don't have to wait around. It'll take some time. In fact, our star, our sun, will actually die long before that happens. But if we were around when the galaxy collides with us, what will happen is, actually there's a really cool little simulation on YouTube that shows what the sky will look like as the Andromeda Galaxy comes closer and closer to us. It won't affect the Earth at all. I mean, the sun's death will affect the Earth. But say the sun lived forever, and the Earth stayed around, it wouldn't affect anything, because the stars in our galaxy, as well as the stars in the Andromeda, are so far apart from each other. There's so much space between the stars that the probability of two stars colliding is so small. So when the galaxies collide, the stars will just go right through each other. Like, there won't be any collisions or anything. It'll just light up the sky a little bit. Like, it'll just be more stars in the sky. How do you find that YouTube simulation? You can, I suppose you could type Andromeda simulation. Oh, actually, Rohit on Astro_SFU is one of our staff members, Rohit. So there's a link there. Okay, cool. So this is the Black Eye Galaxy. What time are we at? 22. Okay, I'm going to... Before we sign off, I really do want to take a look at the Ring Galaxy. This is a cool galaxy. I'm going to adjust it slightly, and then we'll take an image of this. We'll take screenshots and save these images and move over to the Ring Nebula. What am I saying? Did I say Ring Galaxy? I meant Ring Nebula. Okay. Maybe this is better. Move this slightly over. Yeah. Yeah, that's better. Okay. Okay. Ring Nebula, here we come. I hope it's high enough now. It's going to be difficult. It's really low in the sky. But last night I was able to see it at around this time, so hopefully it's gone above the building that's right there. Okay, so as I said, the Ring Nebula is the remnant of a dying star. So the star became a red giant. Its outer layers started flowing away. So as I mentioned before, the outer layers are going to be mostly hydrogen, because when a star burns fuel and performs nuclear fusion, it only does that in the core. So the outer regions are mostly hydrogen, and the inner regions will be these heavier elements. So first it'll create helium, and then helium will fuse into carbon and oxygen. So the inner regions of this nebula will have oxygen, and the outer regions will have hydrogen. So let's take a look at it. Hopefully it works this time. Clear. And we can have a shorter exposure. Wow, there it is. Oh, this is cleared again. We'll do a clean one. 20 seconds. I've seen these objects like a billion times, but I never get tired of it. It's so, so pretty. Okay, so let's adjust these images a little bit. It's nice that we can adjust this in real time, actually. Okay, good. The stack is working. The black level, red level is too high, green level is too low. Okay, there it is. Isn't that beautiful? You can see the different colors in this nebula, and it's just like I said. So, okay, so when gases are lit up and they're heated up, they're energized, they glow in certain colors. So hydrogen, the bright, like, so actually, if you've ever done the physics workshops at SFU or an astronomy workshop, if you've done an astronomy workshop, then you probably would have seen these gas tubes that were lit up. So we actually, sodium lamps, light bulbs that are sodium lamps, they will also light up. Like, it's just gas that's lit up. And when you look at, if you like put that light through a prism, you'll see that the gas emits light in specific colors. Like, it's not the whole rainbow. It's like, you know, the hydrogen will have a really bright red line and then some dimmer bluer lines. And then when you add it all up together, you get a red light. So hydrogen shines mostly red. So it's the brightest line that we can see is in red. So the outer parts of the ring nebula are mostly hydrogen, and it's glowing red. So that's what we can see. The inside, which is where which is like the remnant of the core part of the inner insides of the red star that's floating away. That's glowing in blue, and that's because oxygen glows in blue, and the inner parts of the nebula reflect that, you know, the core is where stars form heavier elements like oxygen. So oxygen, for those of you who are astronomers or physicists, this is the oxygen doublet, the 5007 angstrom line, and the red is H alpha. But anyway, so yeah, so the red is hydrogen and the blue is oxygen. That's what we're seeing in this nebula. Isn't that pretty? It's so pretty. I never get tired of seeing it. Let me just adjust this a little bit more. Okay. Okay. Oh, Godwin, good question. Is this actually a sphere or a ring so it happens to face us directly? So it's actually a sphere. So we are looking, so the gas is thin enough so that when we're looking through the center we can see all the way through. But you can see that the outer layers, the red layers, are where, you know, there's more gas, so it's thicker around there. So it does look like a ring, but it's actually a sphere. We're looking through a sphere. It's very, very pretty. I agree. Do I have time for Orion? Actually, Orion has already set. It's set around sunset, actually, unfortunately, so we can't look at the Orion Nebula. Is the nebula from a single star in our galaxy? Yes. In fact, you can see the remnant right in the center. This star is the star that's becoming a white dwarf right now. Did I say we can live there? No, I don't think I said that. I don't think we could live there. Oh, oxygen. Oh, you said there's, okay. Good question. There is oxygen in there. It's shining in blue because it's oxygen. But the air, like the gas, is so thin, it's like a few particles, like a few atoms per meter or something like that. It's like definitely not livable. So on the Earth, it's something like 10 to the power of 23. So it's like 10 to the 10, a 1 with 23 zeros after it. That's the number of particles there are in like a, you know, a certain region of space in on Earth. Whereas in the Ring Nebula, it would be a lot thinner than that. We wouldn't be able to breathe it. Okay, so yeah, the oxygen is literally, atoms per cubic meter or something like that. I don't know the exact number, but nebulas generally tend to be very, very thin. Okay, so how is the image doing? It's beautiful. It's such a colorful, very colorful nebula. Yeah, we were able to stack for 5 minutes. That's pretty good. Just adjusting things a little bit, make the image prettier. Yeah, so that star in the middle is a white dwarf. So what's a white dwarf? A white dwarf is a star that's made of largely carbon. So it's actually the remnants of the core of the star that used to be, the star. The red giants, the outer layers do float away like that, but what's left over is the core of the star where all the fuel turned into carbon and oxygen, but it's mostly a carbon remnant. It's called a white dwarf. It'll eventually, it's still glowing because of the heat, but it's run out of fuel. It's not going to burn any more fuel, and it will just eventually die out. So how big would our solar system be compared to it? That's a good question. I actually don't know. My guess is that our solar system would be a lot smaller than the diameter of the Ring Nebula. But that's a very good question. Should we look it up? Let's look it up. M57. I actually don't know M57 size. What is the size? It's 1.3 light years. Yeah, that's way bigger. That's way bigger than our solar system. I suspected it would be much bigger. Yeah, because it's So yeah, let's go. Okay, let's look at the image though. Let's not keep our eyes off of our beautiful object here. Oh, Saturn is not up right now. Unfortunately, we won't be able to see Saturn. I know, but Saturn would be spectacular to see. It's so cool to see the rings. In fact, it's actually really cool to see with your eyes. So all of these objects, by the way, those of you who are still with me right now, all of these objects that I've showed you, almost all of them except Venus and the Ring Nebula. The Ring Nebula you can see quite well through the eyepiece if we had done Starry Nights in person and you had come to the telescope. You could see the Ring Nebula and you could see Venus. But everything else that I showed you would be super hard. You basically wouldn't see anything. It'd be so hard to do because our eyes are just not sensitive enough in the dark. We definitely can't see color in the dark. So this, even though COVID-19 has been hugely tragic in the world, at least there's a little bit of a silver lining in that we can all together see beautiful objects in the heavens that we wouldn't be able to see with our eyes, actually, because we have a camera and a nice telescope. So I'm glad you all were able to join me tonight. So we do have a few more minutes left. I'll let this keep stacking, and then I'll save an image of it. It's really pretty. Let's see. But even the Ring Nebula that you could have seen in through the eyepiece, it wouldn't have been as clear as this. Like, this is amazing. Like, you would be able to see like a ring, but you could just barely make out the colors. Probably not even at all. Oh, what's my favorite space movie, huh? Yeah, thank you all for coming. I appreciate you coming. Okay, so what's my favorite space movie? I did like Contact. It was pretty cool, very thought-provoking. I thought Jodie Foster acted really well in that movie. I thought that, okay, there's, I'm an astronomer, I'm a scientist. I can, every time there's somebody put something in a movie that's to do with astronomy, I'm always the one a little snickering in the background. Aha, that's definitely not like that, But it was still, I still enjoy space movies quite a lot. So like I enjoy science fiction. I really like Star Trek. I'm a big Star Trek fan. Next Generation and Deep Space Nine and Voyager, they were all my favorites growing up. And what else did I like? I liked Apollo 13. That was a cool movie. Let's see. So Interstellar was cool because of the physics that was involved, like the showing what a black hole looks like through a simulation. That was kind of neat to see. I thought the story was a little too heavy for my liking, but the science was neat. So Mars Attacks I never saw, so I don't know that movie. Oh yes, I did enjoy The Martian. I saw The Martian. It was very cool. I also really enjoyed that. Okay. Any other questions? We've got 5 more minutes left. This has been so fun. I've really enjoyed this a lot. I have not seen Firefly 2010. I did see WALL-E and I loved it. It was so cute and so funny. Have I ever thought about becoming an astronaut? When I was a kid, definitely. It was definitely, I guess I read up how hard it was to be an astronaut, and I decided, well, actually I like space. I could study astronomy instead of becoming an astronaut. So that's what I did in the end. But of course, if I ever was given an opportunity to go to space, I would totally take it. It would sound amazing. Is there less air pollution due to COVID-19? I don't really know that. You'd have to ask a meteorologist about that. I'm not. I haven't been taking any exact measurements or anything about how much it's affected astronomical measurements at all, so I really can't answer that question. Yeah, I hope Starry Nights will come in person again too. I'm sure it sounds like things are easing up, so we'll start to be able to meet in smaller groups. But Starry Nights is usually a larger group, so that it might take some time before we'll be able to start that up in person again, but hopefully not too long. What makes the outer layers of the white dwarf float away? Oh, that's a good question, Morgan. So it's the outer layers of the red giant. So a star's life is basically a tug of war between pressure and gravity. So when there's enough fuel inside the center of a star to create heat and pressure, then that balances out the gravity of the outer layers falling onto the star. But eventually, the core, when the core burns hydrogen into helium and it runs out of that, then it starts burning helium, but then in the core, but then there's a layer on top of that which is burning hydrogen into helium, and so when it keeps doing that, then you get these onion layers of different layers burning different elements into heavier elements, and then those elements create this pressure that eventually wins outside The outer layers eventually experience more pressure pushing outward than gravity. Okay. Wow, these are great questions everybody is asking. Shooting the Owl Nebula and Hydrogen Elephant tonight. Oh, wonderful. Yeah, so now that we've figured out how to do this is the first time we've done this live stream, and now we've got the hang of it, so we'll probably be doing more of these in the summer when there's good weather. So keep your eye on the website of the Trottier Observatory so you can see when we announce the next one, or you can subscribe to the mailing list, or you can see the news on. We also have a Twitter feed as well as a Facebook page. So definitely keep an eye out for when our next announcement will come. And once again, if you are part of the loyalty program, you can receive credit for this as long as you, within the next 24 hours, until midnight tomorrow, send a list of the objects that we observed tonight and a photo of your stamped loyalty card to the address that's on the page. So it's SFU Science Outreach at sfu.ca. So credit can only be given to those who already have a loyalty card from a previous astronomy workshop. So thank you everybody for coming. This has been so fun. Well, let me just save this. I'm going to make sure that these images get posted somewhere so that you can all remember tonight. This has been so fun. I'm really glad you joined me. All right, so I am going to sign off right now, and if you have any further questions, please send an email, and hopefully we'll be able to keep in touch. So, and also keep an eye on the website for further announcements for more of these nights. All right, good night.